Hello, everyone, and welcome to our workshop on Julia package development. I'm Tim Holy, and I'm going to be giving the sort of introductory presentation today. We're going to be talking about tools for improving package development in Julia. So if you're like us, you are very happy about the many ways in which Julia's package ecosystem is really exploding, and fantastic new things are happening all the time in that space. And those improvements are coming, of course, from a great deal of excellent human effort and new tools that many others have contributed. Both Shuhei, my co-presenter, and I have done some work on adding to that armamentum of tools we have to make Julia packages better. And a lot of our focus has been on let's say, surfacing things that have been a little bit difficult traditionally to understand what's happening under the hood, and make that a little bit more apparent to the wider community. And so today we're going to be discussing, essentially introducing some of these tools. The main focus today is a fairly pragmatic one, and that is of really teaching you how to use the tools. And so in the part one of this presentation, we are going to be introducing you to some of the background in Julia. And this is really, in a sense, a tutorial on Julia's sort of inner workings. And one of the things that's worth saying is that there's a fair amount of technical information that underlies Julia's working. So we're going to be talking about things that I think many of the people in the community know lots about: methods, types, and dispatch, and specialization. We're going to get into some of the details of how Julia dispatches to methods, how its compile chain works, how it stores the code, what it has to do to keep track of code, and caching it. One of the things that's worth saying, I think, is that all of this material is useful to know in terms of appreciating and understanding the implications of the tools that Shuhei and I have developed. But also keep in mind that you don't have to understand all of this to get started using these tools. In fact, the act of using these tools can sometimes help you gain deeper insight into what's going on in the hood. So if you don't understand everything in this background part of the talk, don't worry too much about it. Give the actual tools a try, and they'll probably teach you a lot about the things that you may feel that you're missing right now. In addition to these sort of things about Julia's functionality in general, I'll be introducing one package in this sort of first 25 minutes or so, the method analysis package. And the reason for introducing that package during this introduction is that it lets you see a lot of the sort of what's happening under the hood directly. Okay, so most of you are watching this probably know that Julia has a very powerful dispatch model. It's one of the things that we like about it most. Programmers can create a function, and then they can specify multiple methods for that function. Those methods differ from one another both by the signature of the types that they accept, and also by the implementation, meaning what they do with the data that they are passed, that gets passed to them. Now, we're going to talk a lot about specialization, and we want to distinguish two types of specialization. We're going to call the kind of specialization you see here implementation specialization, meaning these are the different methods for a single function that the developer may write for. This is specialization that you provide by hand. We'll use that to differentiate from another form of specialization, compiler specialization, which you'll see on the next slide. And if you've been using Julia for a while, you're familiar with the fact that Julia, when it's asked to call my round, will identify what's the most specific method that matches the types of the arguments that I'm supplying to it. And this most specific matching is actually somewhat complicated. We're not going to need or get into that aspect in any way today. So in addition to the implementation specialization that developers perform, the compiler performs its own form of specialization. And that's because many of these methods are written with abstract types, or sort of a generic catch-all categories of objects. And even though you might be able to write a consistent implementation for them, under the hood, they often have to differ in concrete ways. So for example, if you try to round a float 32 versus a float 64, the actual bit level functionality of what goes on has to be different. So Julia ultimately has to generate different code for those two different types of abstract floats. And so in order to handle that, the compiler performs an additional layer of specialization whenever you invoke the method with a new type. And so, for example, you don't have to write these yourself. It creates these method instances, as they're called, to distinguish them from methods. And these are specialized for particular concrete types that are passed into these functions. And you can have multiple method instances that are all created from the same method and are, in a sense, sort of attached to that method. Now, so in order to support the generation of efficient specialized method instances, Julia performs a process called type inference. And effectively, if you write your code in general terms like shown above here on top, it will turn that code after performing type inference into something like the bottom. If you've passed in, say, a vector of float 32, essentially what Julia does is goes through and annotates the type of every single object that your code has to work with. And then it compiles a specialized version for that set of types. If you then later on pass in another list, say with a vector of float 32 or an int or something else like that, it will compile specialized method instances for those, right? So this process of type inference is a key step in the process of compiler specialization to generate efficient code for methods that may be written more generically. And the key thing about type inference is that Julia is able to calculate the types of all of the intermediates, or at least when things go well, all of the intermediates from the types of the input arguments. And so this is a very important concept with regards to how Julia then actually calls function, the process of dispatching to particular methods and method instances and the compiled versions of them. And so you probably know that ultimately every bit of code that needs to be executed on your machine has to be compiled down to raw CPU instructions. And so you can think of these compiled functions ultimately as sort of a blob of native code that lives at a particular memory location on your machine. And Julia has to be able to pick the correct blob to execute. And so when Julia calls a function at the very lowest level, there are really essentially just two steps. One is to prepare the arguments, and the one that we'll put most of our focus on today is the process of deciding which specific compiled blob to use. An analogy that I like to use is the process of looking up someone's phone number in the phone book, where Julia has method tables, kind of like a printed phone book. And it has to literally scan through the method tables in a smart fashion in order to find the best matching method. And the process of deciding which method to call can be made at different times. And the sort of extreme versions of this are either at runtime while your code is executing, or during compile time when Julia is compiling your function. And there's a certain sense in which the compiled version looks a little bit simpler. A schematic of how that process works in sort of a pseudo Julia would be that it has to push the arguments onto the execution stack that gets them ready in a form for the blob to pop them off and start processing on them. And then it just transfers execution to that particular compiled blob that it's looked up here, this 52383 blob, and transfers execution there. And then when this thing finishes, it will return its value in a way that the caller can make use of. So this would be what a compile time call might look like. If Julia has to dispatch to your code at runtime, then there's an additional step. And that step is figuring out which blob to call. So you can imagine, it's not called this, but you can imagine that there is a function called getBlob for the argument type, so the specific function that you're calling, and then using the types of the arguments that you're specifying, Julia will go scanning through the compiled blobs, looking for an appropriate one. If there isn't a good match to it, then it actually has to compile it at that point. Ultimately, then it returns the blob, and then Julia can prepare the arguments and transfer execution to that compiled blob, right? Now, it turns out that these are actually, in a certain sense, two extremes. There are a couple of important intermediates, and one of these important intermediates is called union splitting. And this is something that happens when Julia can't determine a unique blob that applies to your call, but where the list is deterministic. It knows it's one of only a couple of options, basically. And so this has elements of both runtime dispatch and compile time dispatch. And specifically in this case, it will check the argument types. But in this case, it doesn't have to use the generic machinery to go scanning through the tables of methods. It can simply check to see if the argument types match a certain predetermined pattern of one of only a few patterns that are possible. And if it matches that one, it goes to one particular blob. And if it matches the other option, in this case where there are only two, it goes to the other blob. And so there is some runtime dispatch here. It can go to one blob or the other. But I think the really key point about this that makes it a little bit closer to the compile time lookup is that the blobs themselves have been pre-generated and looked up ahead of time, so that it doesn't have to do that process of scanning through the method tables at runtime. There's a very closely related concept that I call world splitting. I don't know if there's a standard term for it. I know that one, I think, isn't. And the idea there is that this is something that's applicable under circumstances where Julia actually can't prove to itself what type an object might have or limit it substantially. But if it turns out that in the entire world of methods, there is, say, only one or only a two, something like that, right? Possibilities that it could be, then Julia is going to make a guess that that's the one you'll end up calling. And so in that case, in this so-called what I call world splitting, it will check to see if your arguments are of the expected type. It's the only type that there's actually a method for, and then if that fits, then it will call the expected method. But then, in order to generate a method error, it will try to do it by generic runtime dispatch. Okay, so these are two important intermediates that sort of are in between full compile time and full runtime dispatch, but they share a lot in common with the compile time dispatch in particular. So as you might gather at this point, Julia actually goes to some effort in almost any circumstance where it can plausibly do the dispatch at compile time, or at least the method lookup part of it at compile time, it does so. And the reason for that is that the process of looking up the proper blob is slow, right? And that it would be a penalty on your runtime performance. And so in order to save that time, it does it ahead of time. And of course, there are circumstances where Julia can't figure out the types in advance and it has to make the call at runtime. And so it's actually worth, I think, having at least sort of in the back of your pocket a rough guess of how long the dispatch takes. And there actually isn't a universal answer for this because it depends entirely on how complicated the method tables are. But sort of at least the numbers I tend to work with, I sort of a ballpark use about 30 nanoseconds for a runtime dispatch for a single argument function, and it grows, fairly quickly with methods or with functions that have lots of methods and multiple arguments. Okay, so whether these numbers are dreadful or wonderful depends on your use. If you're only going to do it once, you'll never miss that 30 nanoseconds it takes to figure out which method to call. But if you're calling it billions and billions of times during the execution of your operation, then this can become a significant drag on performance. And so you want to, under such circumstances, do what you can to avoid runtime dispatch wherever possible. Another, and we'll talk in this workshop about some of the strategies for doing that. Another thing that's worth pointing out then is that, as you might gather by this point, there's really quite a lot of analysis that goes on when Julia prepares your code for execution by compilation. So it's really quite an expensive process. And you wouldn't want to have to recompile the same method over and over again for exactly the same types. And so in order to eliminate this within a session that you're running now, Julia will cache the compile code, save it. And these are saved in sort of two broad categories. The method instances, these are the compiler specialized versions of your methods that are type inferred, for example. And then as it moves all the way towards native code, it saves things in a structure called code instance. And basically, you can think of these caches really as essentially the method instance cache, especially as if it were sort of a dictionary mapping signatures, meaning you know which function you want to call and you know the argument types that you want to apply it to, but you don't know where it is otherwise. So this would be a mapping from the signature of the function to to a specific relevant method instance, basically. And once you have that, then you have all of the information that you need in order to make the call. And so one of the nice things about Julia is so much of the compiler is written in Julia, and so it's quite straightforward to see the methods. So for example, here I'm going to do a little live demo. Julia has a function called search sorted, and Julia has long supplied the methods function, which allows you to see all of the methods that are available for search sorted. And so here you can see there are 4 methods that differ by their signatures, but you can see that these signatures are fairly generic, right? And Julia doesn't come built in with tools for looking at a deeper level, but you can get to that by loading a package called MethodAnalysis. And like methods, this has a method instances function. And so if you load that package and then you ask in this running Julia session that's underlying this presentation here, how many method instances are there of search sorted? And so you can see there are 3. You can see they're compiled for specific concrete types, right? These are not abstract types like the signatures of the methods themselves. You may also notice that this is only 3 method instances and we had 4 methods. That's because Julia doesn't generate method instances until it needs to. And so only 3 have been used by Julia itself so far in the process of, say, bootstrapping itself during build or other things to load packages, for example. We can, of course, force compilation. So you may have noticed that there's a method for search sorted for abstract ranges, and there's no such thing here. So let's just force that. I'm going to execute search sorted on a range object. And then now let's call method instances again. And now you can see that there are 5 method instances rather than 3, as there were just a moment ago. And they include, unit range methods as well. So this essentially, as you execute and code in your session, the number of method instances is likely to grow, and that reflects the work of compilation that Julia is doing. Okay, so a key point about these method instances is remember that they do get in cases where the dispatch can be resolved at compile time. Ultimately, these dispatches get essentially hardwired into the code, right? And one of the other lovely features of Julia is that it's a dynamic, interactive environment, and it allows you to redefine methods. And the one conflict that comes up under such circumstances is that if you do redefine a method, since all of those blob addresses were essentially hardwired into the callers of that method, they all need to have those links updated to the new version of the definition. And what makes that possible is that Julia keeps track of all of the compile time callers of a given method instance, and these are in a field called the backedges of that. And method analysis allows you to see those back-edges here. So I'm going to grab a slightly different method, the isSorted method here. I'll show you. I'm just going to pick the first method instance that comes up for that one, and then which you'll see is sorted for a vector of symbols here. And then if we look at the so-called direct back-edges, this is supplied by method analysis. You can see there are only 2 direct callers of this particular method instance. However, that's not the full list of callers, because if we can also look at all of the back edges, meaning both the direct and indirect back edges of this, and you can see there are about 530 method instances ultimately that make use of that particular method instance. So it's quite a lot of code that ultimately ends up making use of that method instance. Sometimes it's a little easier to understand if you represent that call chain as a tree, and so method analysis supports the abstract trees API, and so if you load that package and just print the method instance as a tree, what it prints is a tree of the back edges, basically. And so here you can see the actual calling sequence of the individual methods that make use of it. So there's a lot of data when you start sort of poking into the details of what the compiler uses and stores and all. You end up discovering that there's an awful lot under the hood, and it can get to be fairly complicated. And so one of the nice things then is to have code that can analyze code and back edges and all these other kinds of things to help you figure out what's going on. Another topic that I want to very briefly mention. It's not going to be a focus of this workshop in any substantial way, and that is about invalidation. So we talked about the fact that you can redefine a method, and what I mentioned that it would have to update the links. The way that actually happens is that Julia will do something called invalidation. It just marks those old method instances not eligible to be called anymore, and so that then forces it to say, well, now it doesn't have compiled versions of the necessary methods, and so they will be compiled the next time you make use of them. And you can see that process here. So if I define a function and I define a tuple, and then I call map on all the elements of the tuple with this particular function, and I measure how much time it takes. If you want to measure the time of compilation, it's often best to do things very manually, just because even the convenient macros will often force compilation. So here you can see that this took about 20 milliseconds or so to execute the first time. If we do it on the second call, you can see it's fast. It's actually much faster than I can reliably measure here. But if I then go about and redefine this method, this particular method that I'm supplying to map, so this is a new equivalent in its actual impact, but just a new instance of that, then you can see it's once again slow, because it had to go about recompiling both F and map, making use of F. And so one of the places where this process ends up rearing its head fairly often is in this process of so-called world splitting, right? Remember that I introduced that topic by saying if you were calling a function and Julia wasn't able to predict the types of the arguments, but it knew that there was a very, very limited list of functions that might be called, it's going to make that guess and try to sort of hardwire in the lookup there. And so what this means is if you load in, let's say, another package that extends F in a way by adding a new method to it, and it's of course for a different type, now all of a sudden, Julia is living in a different world, and the proper way to split it is different, and so the code doesn't acknowledge it, and the outcome of this is invalidation. And just because it does strongly influence latency, which is one of our main topics, I'll mention that this can, this has historically been one of the reasons for latency in a lot of Julia code. In the most egregious cases, you can actually invalidate the code that Julia uses for loading the next package, and that ends up needing quite a lot of recompilation before you can even start loading the next package. We've, I think, made a fair amount of progress on this problem during the development of Julia 1.6, and it was one of several different factors that went into contributing to reducing the latency in Julia 6. This invalidation is not a huge focus of our discussion today, because a lot of the work on invalidation was done in base Julia itself. I'm really trying to make sure that this is directed at package developers, and at least until precompilation becomes more widespread, package developers may not have to fix invalidations in their own packages as much. And moreover, a lot of the other things that we're going to be telling you about today will essentially inure you from invalidation, because we'll give you tools to help you reduce the number of times that you're making calls with unknown types. And that's really the main and most effective way to eliminate the possibility of invalidation. The last thing that I wanted to cover in this introduction is a role for backedges. So a second role for backedges, and that second role is in a process called precompilation. Many of you have probably seen messages about precompiling when you first, let's say, install some new packages. And what ends up happening, right, is that Julia is loading those packages, generating a lot of lowered code and some type inferred code, and then it's caching them to disk. So, and that caching to disk means that not only are you avoiding recompilation within a session, but you're also speeding up the process of making use of that code in the next Julia session as well, next time you restart Julia, let's say. Now, so this process of precompilation, caching method instances to disk is actually a little bit complicated, and one of the obvious reasons why this has to be complicated is because method instances, as you've seen, depend on a lot of other method instances. And if the only thing that Julia did was cache the very top level methods in your method instances in your package, it wouldn't really help all that much. And so a really key step is to cache the things that Julia depends on, that those method method instances depend on. And so how do you go about doing that? Well, so when you precompile a package, Julia is storing the so-called lowered code. If you're not familiar with that concept, we'll introduce that later on in today's session. And it will also store the type inferred code for the methods that are defined in the package. So the methods that your package has added, those all go in your package, basically, right? And if you've called them at least once or precompiled them, then the even type inferred versions go into the package. But importantly, any method instances that weren't already available also get stored. Okay, and so now Julia isn't going to do this exhaustively, just because loading method instance for every possible type, there's no real even way to do that in principle. And if you tried, it would actually slow things down, because there would be many theoretically possible method instances that you could cache. And so in the end, the programmer, the developer of the package, really has to do something to specify which method instances with type inferred code should be cached in the file. And there are really two ways of doing that. The most sort of widely understood one is to have explicit precompile statements where you say, please compile this function for these argument types that will generate a method instance. And if that's for a method that your package owns, or a dependency of a method that a method instance that your package owns, then it will cache it to disk. And so it's worth knowing that even though this says precompiling it, it really is literally just precompiling it. It's not saving it to disk at that point or anything like that, right? And so this just simply forces Julia to prepare the method instances and their backedges. And so the implication of that is that you don't actually have to issue explicit precompile statements if you want to reduce the latency and cache more code to disk. All you have to do is execute things during package build time, basically, and that has similar consequences. And so we'll get more into that process of precompilation a little bit later on. I now just want to summarize this overall introduction. There were a couple of key themes that we hit. The process of method lookup is slow, and Julia circumvents that slowness in many circumstances by being able to figure out what all the types of all the arguments are, and that allows Julia to move the lookup of the appropriate instances to compile time. Of course, in order to exploit this, it has to specialize, do compile time specialization for methods with concrete argument types. Since that process of compilation is slow and sometimes many different instances of a single method get compiled, you want to cache those to disk, and that caching process is interesting. We'll talk about it in greater detail a little bit later on. But both the methods to save the cache and perform code and validation actually overlap at the level of these backedges. And so for the rest of, we're going to pause for a few minutes and maybe answer any questions that have appeared. If there aren't any, we'll move straight into the next presentation. But just simply to say, where are we going to go from here? And the thing that this introduction has hopefully shown you is that there's an enormous amount of detail that's available at the level of Julia itself about the compilation process. And because compilation does really a very exhaustive analysis of code, it sort of spying on the results of that compilation provide an opportunity for understanding opportunities to perhaps improve the code further. And that really is the fundamental theme of what Shuhei and I have been working on, and that is, how do we exploit the analysis that gets performed during compilation in order to provide package developers with tools to make their packages better. And so with that, I will stop my sharing and turn things over to Shuhei. Or see if there are questions.
Yeah, we have some questions. And can you see it Pigeonhole?
I can see, oh yes, I do see questions.
Yeah.
Okay, so let's see here.
Yeah, so the highest vote is, does Julia look into the method instance cache first before searching through the tables? Cannot that also end up becoming extensive?
Okay, no, so right. So what Julia will first figure out which method to call, and then it will it will use the process of searching the individual method instances. So each method keeps track of the associated method instances, and so that's the order. First find the method, and then find the method instance. Since when has Julia had world splitting? I'm not sure I can remember exactly when that got introduced. I'm going to guess, maybe someone else would know and respond, but I'm going to guess that was introduced somewhere around maybe 2017 or something other like that. Yes, and I see you've answered one of the questions at the level of text also. Okay. Why? Why is caching? There's another important question. Why is caching with several votes? Why is caching method instances preferred over generating binary executables? So you can do that with package compiler, but Julia's native mechanism is focused on the interactive development of code, and so for that you really want to have these essentially independent living blobs that you can mix and match in different ways. And so the method instances, which is the type inferred code, is the farthest that we've gotten thus far in addressing in the caching problem. That doesn't mean we'll always stay there, but in the long run, that it's a big step along the way, basically. So it would be nice to also cache the native code for each individual compiled method instance. Hopefully, we'll get there. We'll get there eventually. But for right now, it's the type inferred code that gets cached. All right, Shuhei, do you want to take over?
Yeah, I will take over. So I'm going to share my screen.
Oh, am I still sharing? I'm going to remove this from the stream. Okay, that.
Mm-hmm. Okay, so can you see my screen right now? Yeah, I think I'm sharing my screen. So yeah, let's start my section. So yeah, I'm Shuhei, and I'm a research programmer working at Julia Lab at MIT. And in this section, I'm going to introduce JET.jl, which is a static code analyzer I developed recently. And yeah, I'm introduce this package in this section. Okay. So I switched to the presentation mode. And yeah, okay. In this section, I will first explain an overview of JET, as well as its motivations and the basic ideas using simple example programs. After that, I'm going to see actual usage example of JET on the real world package. Especially, I will take macro tools as a target package. Next, I will explain the concept and the usage of JET's performance linter and the difference between JET's default error finder and the performance linter. Lastly, we will run the performance linter on JuliaCompiler itself and try to improve its performance slightly. So please open JET's notebook, and you can run the code with me. Okay. So what is JET? JET is a code analyzer for Julia, and JET can take an ordinary Julia program and automatically detect possible error points. And there is no need for additional setups. So how it differs from the existing tools? First, JET's analysis is based on type inference, and so JET doesn't require any additional type annotations just for the sake of analysis. And this is a very unique aspect of JET, since usually other dynamic languages like Python or JavaScript introduces static analysis using the method called gradual typing, where static analyzers require programmers to annotate types. in order to enable static analysis. And secondly, JET offers a first-class metaprogramming support. Although Julia is one of the most expressive programming language, and its metaprogramming features are very widely used in the community, but at the same time, metaprogramming features are very common obstacles to static analyzers in general. Still, JET handles metaprogramming features very well using a technique called partial evaluation. So let's get started. JET is an unusual Julia package, so you can just install it from Julia's general package registry and then simply using it. And as a specific setup for this workshop, here we define this utility macro called report top level, which takes arbitrary Julia expressions and runs JET on it. Usually we can simply run JET directly on a file or package, but since we are going to use the notebook environment during this workshop, we will use this macro instead of switching between this notebook and an editor. The definition of report top level macro is really not important, so let's skip its detail for now. As a first example, let's run JET on this simple but very inefficient function that calculates the number of the numbers in the Fibonacci series. Oh, sorry. So there are a couple of things to note here. Firstly, JET successfully found an error that will happen when we pass a string to the Fibonacci function here. But also note that this function is very inefficient. So for example, the call of Fib 1000 at this line won't terminate from the beginning if we actually run this code snippet. So how is that possible? This example actually illustrates the fact that JET analyzes an input program only on type level, and it doesn't require, it doesn't actually execute it. So in other words, JET analyzes your program statically, and so its analysis is really different from anything involving runtime, for example, usual testing or whatsoever. So to see the difference better, let's consider this example. This function takes an iterator and tries to pass its element into floating numbers and then sums up successfully passed elements. Let me clear my result at first. Okay. Yeah. So as for this specific input here, it works well, and seemingly there is no problem within this function. But let's see what JET says on it. So JET runs this code, analyzes this code, yeah, and it reports something. So JET complains something. Why? The key point here is JET is designed to account for all the possible program executions. And so if we look at the parse sum function carefully, we can see that argBars here is actually an untyped vector, and that is a vector of any typed elements. And so actually Julia doesn't understand what the call of some argBars here should return when the argbar is empty. This case didn't happen for the specific input case we tested above, but it can certainly happen. So in other words, JET found a possible error ahead of this time. JET found this possible error ahead of time before we end up seeing that on runtime. This is one of the strongest advantages of static analysis, and that is it can find errors that we may miss to cover otherwise. And thanks to JET, we can make parse sum function more robust by initializing argbars as a typed vector like this way. And then JET doesn't complain anything. So here are some observations so far. JET can reason about all the possible program executions, so it can find possible errors that our test cases may not cover yet. And this feature of JET is particularly useful when you are defining a new type that implements some interfaces that we can use it for existing generic functions. So as an example, we define a new type called squared here, which behaves like an iterator that uses squared numbers. We define the iterator and length interface, and then seemingly it works correctly for the existing sum generic function. But JET should tell us that actually we have the same problem as our pass sum function before. So, oh, sorry. Yeah. So JET reports the same error here as before. This is essentially because Squared actually missed to implement one more required interface. That is, we need to implement the L-type interface so that Julia can understand what to return when we call sum on empty squared. So yeah, we can define L-type here, and then JET doesn't report anything. So here's a recap. Julia doesn't guarantee the functionality of an input program, and we Julia programmers have to make sure it works by ourselves. We usually use test for that purpose, but test may not cover all the possible executions. JET can check the quality of generic code in a way that doesn't rely on runtime, so it can find errors that otherwise simply get ignored. Now let's discuss the second important feature of JET. Julia programs make a heavy use of its metaprogram features, and I think Julia's powerful metaprogramming features are the key of Julia's extreme expressiveness. Julia currently supports mainly two stages of metaprogramming, eval and macros for abstract syntax level code generation, and at-generated function for metaprogramming at inference stage. We usually use eval to eliminate syntax level duplications and macros to implement a simple domain-specific language or enable some optimizations using syntax level information. I think this code snippet adapted from Julia base is a nice example of eval usage, where we define similar functions that share the common structures all at once using for loop. But on the other hand, static analyzers in general suffer from this kind of code. That is because it has to actually execute parts of programs that involves eval, even though they are static analyzers. And also, it needs to expand macros to get a correct semantic meaning of input programs. But again, macro expansion also contains actual program execution. So how JET handles metaprogramming? Actually, JET partially executes input program so that JET can understand all the definitions of a generic function or struct or whatsoever. But at the same time, it doesn't execute other portions of input program that are basically usages of functions. For those parts, JET analyzes them statically instead, as we have seen so far. Since JET's static analysis uses a technique called abstract interpretation, I use concretization when referring to JET's partial evaluation of those definitions. So in this example, adapted from above, JET actually executes this for loop because it includes a bunch of definitions of generic functions. At the same time, it doesn't execute succeeding their usages, but JET analyzes them statically instead. So as a result, JET can correctly analyze this program, although the static analyzers like static static lint.jl will not be able to reason about this program correctly. Similarly, macros are fully supported. JET understands macro definitions and simply expands all the macro codes appearing within input program. So this def_v macro introduces new global variable named v when it's expanded, and JET can just understand it and so won't report any false positive errors of undefined global variable name there. If an error happened during concretization, JET simply reports that error that actually happened in program execution. In this example, there is a typo, and this macro expansion fails there, and JET just reports it accordingly. There is a downside of this approach, though. So JET is not really safe. It's not fully static, and so its analysis may involve actual program execution of user code. So, for example, if a macro expansion never terminates, JET also never terminates, which I think it might be a potential security risk when JET is used within IDE in the future, for example. There is also another special macro named @generated function, which allows us to intervene into inference and do some code generation using type of information. Generated is used for advanced optimizations or for executing programs and different program semantics, like what reverse mode auto differentiation does. This is another example adapted from Julia base, where this match function uses generate function in order to exploit the fact that the element names of named tuple can be known at compile time and implement efficient merge functionality so that it can eliminate some runtime queries of element names. But the problem is staged programming or metaprogramming in general can be very tricky. And for instance, if we have forgotten to add quote names, a quote node here within the merge function, then it simply doesn't work. This specific error happened because the names here is no longer a symbol and will be resolved as variable name. But I think it requires much knowledge and skills for us to recognize these tricky points of metaprogramming and write correct metaprogramming programs. So, but JET can also help us here because it can perfectly reason about generated function and detect possible errors within them. So with JET, we can just understand this macro this merge function is sort of problematic and where potential error can happen within this function. So as a summary, metaprogramming is one of the most important features of Julia, I think, and it allows Julia to be very expressive. But metaprogramming can be very tricky and a nest of bugs, and even worse, static analyzers in general suffer from it. Nevertheless, JET handles metaprogramming very well because its partial concretization allows it to analyze Julia programs effectively, no matter how heavily they use metaprogramming features. So far, we have used report top-level macro to use JET, but as I said at the beginning, we usually don't use it in practice. JET exports some useful entry points of analysis, so I would like to explain them quickly here. The first entry is report file, which simply analyzes a script. The script is supposed to include both definitions and usages, so we want to use it to analyze test files of a package, for example. The second one is a report package. It literally analyzes the package, and it doesn't require usages to exist in the package. We will use this entry in the next section. So let's leave it for now. The last one is report call and its macro variant. They work very similarly to code type and its family, and are very handy for interactive analysis. Yeah. Okay. Now we have learned the basics of JET. Let's run JET on a real-world package. Here, I'm going to take macro tools as a target package. This is a wonderful package that offers pattern matching utilities and is great for developing complex macros or general AST transformations. It's actually very important for the ecosystem as well. Julia Hub says there are more than 1,000 direct or indirect dependencies of this package. Yeah. We will use report package entry to analyze macro tools here. It takes the name of a package and tries to find a package within the currently active environment and then analyzes the code base. The most important difference from other entries is it doesn't require any usages of definitions. This is very useful because usually a package only contains definitions and not usages. JET will use method signatures to generate stub usages, so it's okay if there is no actual usages. But of course, it may result in less accurate analysis because Julia's generic function in general is defined with abstract signature for good reasons. So this is a mental model of how report package works here. It first corrects those definitions of G and F functions, and then after that, it corrects from, it analyzes G with argument type any, and also analyze function F without any type arguments. This code snippet will clone the source of macro tools into your computer and checks out to the latest commit. If you have already installed macro tools somewhere, please check out by yourself. So I'm cloning macro tools now, and yeah, check out to JuliaCon branch, and I will work on there. Let's run JET on macro tools first. As I said, there is no need for additional setups, so we can just call report package on macro tools and get some results. So currently we have 11 possible errors within macro tools, and we are going to fix it. Yeah, so I will switch to my editor and see what happens. Okay. So I actually installed macro tools here, and I will edit some files within that. It takes a little longer than I expected. Yeah. So yeah, there are some errors reported, and we are going to look at what happens there. So the first one I would like to pick is this pass error. It happens at struct.def.jl file at line 13, and we are going to see it. So JET reports this pass error variable name is simply not defined. And there are 3 usages of pass errors, and so JET also has those 3 errors. I will simply try to find a definition of it. And seemingly, there is no definition of it. I'm going to check the commit where this one is added. GitHub. And as far as I can tell, they also simply forgot to add this function, probably. So I will going to just add this function. I think it's supposed to raise an error. So argument error and expression cannot be print. Yeah, this should be enough. And so now let's run JET again. Yeah, so we now have reduced the error from 11 to 9, and yeah, that is good. We will also see this one. So here, JET reports the build depth is not defined, and we can just regrep it. And there is no definition of this function. So I think this macro definition is actually got stale at some point, and so this macro is not functional at all at this moment. I found this macro is defined in a test file actually. So I think at some point macro tools has forgotten to move this function into no. I think macro tools simply just forgot to remove this macro definition. So I'm going to remove it. There's also another error here. This one could be. Another interesting thing is here. So at this point, JET reports there is no field of named as captures in nothing type variable. It's reported here. So this get property on this captures field is type unstable, and JET cannot understand what's this base match function returns. So Julia compiler understands its return type is like this way, and if this return type is nothing, if this return is nothing, this captures retrieval will be simply raise an error. But actually, macro tools only use this function in a context where this regex match always succeeds. So we can simply annotate this this function return is not nothing, and we can make a type annotation to tell the compiler so that compiler can understand it's never be nothing. So let's run it again. And we have reduced error to not 7 at this point. Yeah. As the last one, I want to pick, this can be tricky. Yeah, this one not be good. Okay. 64. So as a last one, as a last fix, I want to pick up this error. This error is reported from there is no matching method for call signature. That's if we call iterate function with nothing. And yeah, it will raise an error. We can just check it simply because like this way. This function call is simply raise an error because there's no matching method for iterate with nothing argument type. And it reports the reason why it reports here is this split bar function may return nothing because macro tools match macro tries to do some pattern matching on these symbolic expressions, and if there's no matching, if the matching failed, it simply returns nothing. But again, macro tools is this function is only supposed to be used within this match is succeed. Otherwise, this iterate will be simply fail. So we can simply assert it that this function return is never nothing, or we can just annotate it as untuple. In this way, we tell the compiler about this function never returns nothing, and then JET doesn't report anything because Julia compiler just understands this function never returns nothing, so this iterator call will always succeed. But we can also assert this match always succeed, and if it's not succeed, we can also raise an error. Here I'm just annotate it here and check what's JET reports finally. Yeah, so we have reduced, we eliminated 6 possible error points, and now macro tools gets more robust. Okay. So yeah, we have improved some package quality of macro tools by fixing actual bugs and improving type instabilities. So let's move on to the next topic, performance renting. JET offers an instructor for plugin analyzers, actually. And JET's default analyzer that we have used so far is one specific instance of analyzers implemented within the infrastructure. There is another useful example of JET's plugin analyzers, and that is a performance linter. So how they are different? As we have seen, JET analyzer, error analyzer aims at finding possible errors using type inference. On the other hand, the performance linter aims at finding possible performance pitfalls by analyzing optimizations, Julia compiler's optimizations. It currently mostly reports where runtime dispatches will happen at runtime, but also reports optimization failures due to mutually recursive function calls. Let's consider this example. This function f will calculate cumulative sums starting from 1 to n. As a spoiler, this function is really not high performing, because Ri here is initialized as untyped vector, and it causes the succeeding computations to be very type unstable. So yeah, let's run JET on this function call first, and it doesn't report anything. But we can use JET test and its performance linter, and now we can have something. Yes, so JET test's dispatch analyzer, on the other hand, takes dynamic dispatches more seriously and reports it to us. The performance linter tells where the type instabilities are detected, and we can fix it by initializing Ri here as typed vectors instead. So we can fix the type of stability here by initializing Ri with t-type. And now performance linter doesn't complain anything. And this function runs actually probably 3 times or no, 5 times faster than before. And so, yeah, it's good. We should also note that the performance linter is more powerful than manual inspection with code type or code 1 type, because it can analyze the entire call graph and all the calls involved within it, rather than just looking at the final call frame. So say we have this simple function named call f, which simply calls inefficient function f. We can see what's code 1 type macro reports, and see it doesn't present the actual type instabilities. While this performance linter, JET's performance linter detects it for sure. So we can call code 1 type directly on function f instead, and see the same some type instabilities. Type instabilities, but it could be tedious or simply could be unpractical when type instabilities happen in deeper side within the call graph. Now let's see what's the actual usage example of the performance linter. In this workshop, I'm going to run JET test on Julia compiler itself. Some parts of Julia compiler, including type inference or some optimizations, are written in Julia. And so we can analyze those parts using JET. And every Julia programmer wants it to be faster. So yeah, let's take this as an example. I'm going to add some additional configurations to analyze the compiler code. So let me explain them here. Firstly, this function filter ignores type instabilities that come from certain generic functions. This is because they explicitly use dispatch to branch on input types. And actually, we can rewrite them so that they won't be dynamically dispatched. But for this workshop, we are going to just ignore them. Secondly, this frame filter configuration we are going to focus only on code within the compiler. The compiler code actually uses some dummy versions of base functions, and there are some type instabilities within base, unfortunately. But we will just ignore type instabilities within base for this workshop and just focus on compiler code. And core compiler type in function is the entry point of type inference, and we can enter dispatch analysis from this entry function and analyze the entire core graph of Julia's type inference and optimizations. In this live coding, I will also use revise in order to interactively reflect changes made on source code to JET testers analysis results. Please note that you may also see very different results from what I'm going to show from now, depending on your Julia version. This is because Julia compiler code keeps evolving day by day, and since JET deeply relies on Julia compiler, its analysis result can also change depending on Julia compiler. But anyway, let's run it. Let's try it. So we put it here. Okay, I use revise and adapt some code. Yeah, it will take some time, probably around 10 seconds or so. Yeah, so now we have a bunch of reports. JET test says there are 148 dispatch points within the Julia compiler itself. And I think it's not really good, but yeah, we're gonna fix it anyway. So there are many points I want to fix here, but let's take this one. It happens at 1,831 line in abstract interpretation.jl. So let's run it. Yeah, answer 31. Okay, so here JET reports this get index is dynamic dispatched. It understands the second argument of get index. So this one is caller PC at this point is concretely typed. It's just an integer, but still JET doesn't understand its first argument. In this case, the caller source.SSA value types is really untyped, and so it reports this is dynamically dispatched. It's because caller is an inference state, actually, this object type, this object, and its SRC is called info object, which has SSA value types field, which is simply typed as any. This is because Julia compiler has many different forms of program representations, and so code info object can represent many different program representations, including low order code form, typed low order typed low order form, and optimized low order form. But so in this case, we have to tells the Julia compiler about its type by type annotations. So we can extract it into a variable and type annotate here. This is valid because at this point, when in inference, code info object always has SSA value types field as a vector of any type of object, and we can tell that fact to the compiler by type annotation. And I'm going to also fix another point. I will take C at this line, 41 line. Here, its get index is also untyped. So yeah, I changed some change above, so it's slightly changed. But so essentially, this get index function call is untyped, and just reports the error. This runtime dispatch at this point. This is because statement arg variable is very untyped, as it's typed any here, and so this means Julia compiler doesn't understand this variable well. That's why, because statement variable is very untyped at this point. Actually, it's typed as any here, and we have a HD variable which branches on the type of statement variable. That if a statement variable is expression type, it extracts the header field of it, and otherwise it's nothing. So at that point, in this branch, the head function, head variable is enter symbol. So in that branch, this statement variable is always typed as expression. But the problem is Julia compiler at this point is not so smart enough to understand this kind of relational invariance. So we have to tell the Julia compiler about the fact and see tell that fact. So the simplest way is use type annotations like this way, and then this code get index function call will be type stable, and this sort of error won't be reported. Similar things happens in this function, I think. So I'm going to fix it as well, and lastly run JET on it. So for example, this get index call will be also type unstable. We can fix those like this way. Yeah, so let's run JET again. Yeah. Since we have loaded revise into this runtime session, revise will automatically redefine this function, and its causes JET analysis also gets updated. So yes, we have eliminated 6 runtime dispatches using JET test, and yeah, the Julia compiler is now slightly faster, I believe. Yeah. So that's my end of my section. So I will take a look at questions.
I answered a bunch, but there are some that are better left for you to answer for sure. So any of them you want to answer by voice, by all means, go ahead.
Okay, I will pick up some of it. Is there any plan to integrate JET directly with VS Code? Yes, I and Sebastian discussed about it 2 months ago. As far as I remember, I do want to integrate JET with VS Code, and yeah, because current interface of JET, this sort of interface of JET as console output is sort of horrible. So I do want to GUI for JET's analysis result, but simply we don't have much time to work on it. But yes, we are planning to do it. So it's on including static analysis by JET as a part of package. Yeah, we actually JET test is written for that purpose. So you can use JET testers test dispatch macro. Yeah, and using this macro, and this macro will check every dynamic dispatches within this call, and if there's any type of instabilities, it will raise an error, and you can use it for test. It's also integrated with test standard library infrastructure, so you can use it in a test case. Test dispatch. Oops. Test dispatches. Yeah. Yeah, so it's included in test summary, so it's integrated with test standard library. So you can use JET testers performance linter in a test suite, and it could be useful, I believe. I haven't written similar functionality for JET's default error finder yet, but that won't be much hard. So yeah, we can do that. Is there any interesting question, Tim, you found?
There's a highly voted question on whether there are any styles that are so hostile to static analysis it should be considered unidiomatic. I think from my standpoint, I would say that that's almost an independent issue. So the tools we're presenting today really rely on the code being lowerable and being able to at least run type inference on it. And so at that point, these tools are really just looking for flaws in the implementation of that code. But I'm not sure that other than the technical aspects that these tools address the stylistic aspects very strongly. Shuhei, do you have a different view of that?
No, I almost agree with you. And yeah, it's hard to comment. It's really depending on how you want to use Julia. And we don't need to care about type instabilities for casual coding, like scraping or whatsoever. But in a critical situation, we do want to care about type instabilities, and the coding styles will really change depending on the context. And yeah, so if you do want to be friendly with static analysis, you will end up annotating you will adding much of type annotations because JuliaCompiler is not may miss some constraints, but yeah, we may want to summary those techniques, and it can be seen as some idiomatic Julia coding style, but I don't think it can be easily generalized. Yeah.
All right. Maybe in the interest of time, we should move on. We're running about 8 minutes behind right now. So if that's okay, maybe we can respond to more. Do you want to stop sharing your screen real quick, and then I'll switch over to the next presentation?
Sounds great.
Or Okay, yep, here we go. All right, I'm going to switch over now to the next presentation. Can you see my my presentation screen here?
Yes, I'm seeing it.
Excellent. Okay. All right. So I'm going to move on to another tool that's called SnoopCompile, and I'm going to this one's actually going to be kind of split. In fact, we're both sort of splitting some elements of what we want to talk about into a couple of pieces. I'm going to be focusing on sort of the parts of SnoopCompile that don't need the ability to read lowered and type inferred code. Well, we're sort of saving that kind of for the last part of this overall session. So what I'm going to go over is how you collect, how SnoopCompile collects data on Julia's compiler, which is a little different from how JET does it. I'll talk about a couple of graphical tools that you can use to get a very high level overview of what inference was doing and how long it took on your code. And I'll talk about a technique that I think is still in its relatively early days in the Julia community, and we probably need more development of the tools, but which I call profile guided despecialization. And then I'll talk a little bit about precompilation and latency. And just to emphasize more reasons, as Shuhei was mentioning in his talk, about reasons to want inferability, and that topic will as far as SnoopCompile is concerned, be kind of the last topic we cover. Okay, so obviously, you know, the JET and SnoopCompile look like they might be very different from one another. You know, SnoopCompile focuses on latency, whereas JET focuses really on correctness. But in fact, actually, under the hood, there are many more commonalities than there are differences between them. And the key reason is that both of them, and Shuhei and I collaborate on a bunch of stuff together for that reason. A key reason is that both packages spy on type inference as a means of gathering data about code, right? And so, but even, you know, so both the use that they put that data analysis to, but even the mechanism they use to spy on type inference actually differs. And one of the and that's very deliberate, right? So one of the key design principles of JET is its sort of overall safety, and that means that it should be operating at the level of types. But what that does mean is that the operation of the level of types can only extend as far as type inference works. So, for example, Shuhei demonstrated that JET will warn you about an error if you try to sum a vector where the element type is any because of a potentially or of a missing method for 0 of any. But if you pack if you create a function that calls sum on 2 elements of a list, and then you pack such an array inside of another array that has data type any, now all of a sudden it's not possible for type inference to know what type these individual entries have. And so JET will actually, when analyzing this, will tell you that there are no errors in this code. And again, that's very deliberate. It's because JET is trying to do static analysis on your code, and so it goes as far as a break in inference and no further. So SnoopCompile has, so this is sort of the call chain that gets made from this, and because these are both hidden behind an inference barrier, because the element type of this vector of any is any, that means that any static analysis isn't going to peer all the way down in there, because those calls are made by runtime dispatch. SnoopCompile actually has quite a different mechanism for collecting data. It really acts much more like a profile, or it basically turns on snooping, which basically turns on a special mode inside of Julia's type inference engine, and in which it starts logging everything it does, basically. And then you just run your code, and all the while that your code is running, any new inference is getting logged to the log file. And then you turn off snooping to go back to normal execution mode, and then SnoopCompile will return the data on the snooping rather than the outcome of the whatever computation or process you launched. And so we can demonstrate this quite easily. This is the same sort of example that I just showed before. And so we load the SnoopCompile package, and The key macro, I'm not sure it's perfectly named. We may want to change that at some point. Turns on deep snooping, meaning that it's a recursive process of snooping, basically. And so if we execute this cell here, then what you can see is that you get this so-called inference timing node for the root process. This is just a dummy node. The interesting point is that it has two direct children. And just like I showed you earlier on in terms of method instances and their backedges, SnoopCompile integrates with abstract trees to provide ways of browsing these inference timing nodes. And what you can see here, I've restricted it to not recurse deeply into the tree. And you can see that inference was triggered both to compile my sum2 function, because it was a brand new function, but then it also had to compile sum of vector of any. And again, this call was made by runtime dispatch, but and so therefore it's a top level node of the root node, right? Everything that's at the top level of the root node is a fresh entry into inference from either what you just executed on the command line or a runtime dispatch in the code that you launched, okay? And so there are a number. This session, as long as it is not going to be exhaustive by any stretch of the imagination. There's a lot of documentation available for SnoopCompile, and if you want the full story, I recommend reading that. But what I'm going to focus on are some of the graphical tools here. And so I'm going to visualize this as a flame graph, and so you can convert that inference node timing into a flame graph, and then you can visualize it with a profiler. And what you see here now is this is the root node, and the horizontal axis measures the time overall. So this is essentially the beginning of the processes that it executed. This is the end of the process. And you can see that there are two baseline flames, because those are the two child nodes of the root process. And one of them was for the inference of main.sum2 that I just defined, and the other one was to infer sum. And you can the height of these flames is proportional to how the recursive nature of type inference and how far it had to go. So you can see it ended up going into MapReduce and other things that are needed and that you're probably familiar with from looking at Shuhei's presentation just a bit ago. And so you'll also notice that there are some empty spaces, and this is when things besides type inference were happening. So LLVM code gen might have been happening here, or it might have been generating the IR for LLVM, or LLVM might have been generating native code, or perhaps your code was actually doing something useful, right? And so all of these empty gaps here are whenever Julia is doing something besides inference, basically. I want to emphasize that while running it, this is nice for notebook presentations. I pretty strongly recommend that you use profile view, because if you use profile view, if you left click on some of those bars, it will display in your REPL command line the complete method instance with all of the types that were being compiled there. And so that's a nice thing. And if you right click on it or a two-finger tap on a laptop, it will actually open that specific line of source code in your editor. And so you can go and you can take a look at the actual line of code that method starts on, for example, right? And so just from browsing this flame graph, you can get a lot of insight into what parts of inference take time, okay? And I'll talk about other things you can do with that as well. And there's again, quite a lot of overlap with JET, because SnoopCompile, like JET, can figure out which calls are made at runtime and which ones are made at type inference time, specifically, or I compile them, and specifically each fresh entrance into type inference is due to a runtime dispatch. Okay, so let's do a real world example, because this one will take a little while because of the latency issues that we might like to address. I'm going to launch it right now. So this is using what is, I think, currently the highest starred package in the Julia ecosystem, Flux. And this is straight out of Flux's introductory documentation. And so there's a model of the real world here called Actual, and the user wants to try to mimic this with with a dense model. So the user has to define a loss function, which is just based here on your prediction and the mean square error from your prediction, sets up a set of training and test data, and then uses the actual function to make predictions about the values that should be produced. And then we get to this SnoopI deep, and inside of the body of this macro, we set up the prediction thing, and then we train the model on that. Right, and so you can see it's still executing away here because it's taking a while. Now, this is such a tiny problem; it's not due to the sheer amount of data that are necessary in order to optimize this model. It's really most of this latency is simply due to inference time. And I'm amazed at how much slower computers run when they are also video casting at the same time, because normally by now it would have finished. But yeah, so this overall, when you're not video casting, the compile time for all this code is somewhere around 20 to 25 seconds on my particular laptop. It's definitely not over yet. So let me see if this is going. If I go on to the next slide, no, then we're really just going to need to wait for the results here before that finishes. I'm amazed how long it's taking. Well, let me presage what we're going to talk about a little bit. So what I'm going to do, if the time permits it, is display the flame graph here. It's a much larger flame graph, of course, so it'll have many more bars. This is going to illustrate a couple of things. So basically, there were going to be two big inference sort of events, so to speak, that are relevant here, and the one of them is going to be marked in red, and that red marking is of a set of inference runs that are sort of naively not precompilable, basically. And that lack of precompilability comes from the fact that you're trying Julia might naively have a hard time saving this code to a cache file. And the reason basically is that it's operating on methods in a package that are using types that are created by another package. And this is a challenge for precompilation. Okay, we finally have it here. So that is a surprise. Oh boy, let's see. I might have executed it twice, and therefore the inference isn't going to work out so well. All right, well, yeah, so this is not actually what you get when you do it the first time, but just for interest of time, I'm not going to rerun it. What you can see here are things that had to be re-inferred upon second execution. That's relatively rare, but this does at least illustrate the large bar problem, basically. So if I restarted my kernel, then I would be able to do it. Well, yeah, no, I think I better move on just in the interest of time. I'll see if I can launch that and show the actual result later. So under the takeaway from this overall was that about half of the time was spent on type inference, and a lot of it is red, and that obviously is a big problem. Oh, I may not have mentioned. Let's see here. In showing you this, I meant to mention one thing. So not only is it showing you these nodes of the specific method instances that got compiled with the number of things that they directly called, but it's also showing you two numbers. And these two numbers have a specific interpretation. The first one, for everything, the root node is a little different, but for every normal one, the first number is the sort of self time, meaning it's the amount of time it took just to infer that specific method instance without any of its callers. And the second one is the inclusive time. So just the time that, or the time that it took to infer the method, including the fact that it had to also first, before it could finish that process, run inference on all of its dependents, basically. And so the inclusive time is second, it's the bigger number. Exclusive time is essentially, the whole thing minus what all of the callees that it had to infer, and that's what's left basically as the exclusive time for that particular method. Okay, so this is the flux example is not entirely realistic, unfortunately. About 25 seconds was spent on executing it. More than half of that was inference. And the profile would identify just even one single method that is precompilable that would shave about 3 seconds off of the execution time. So that seems to be well worth it. And so one of the things that I also want to show you is that there are several techniques for reducing the amount of time it takes to do compilation. And the main technique that I want to show you there is a technique that I'm calling profile-guided despecialization. And I want to switch over here to a REPL session. And I want to include, and in fact, here, let me first show you the code itself. So this is going to be a demonstration that I'm going to make on static arrays. So static arrays, many of you may know, is a wonderful package that allows you to speed up the processing and computation speed when you're doing a lot of operations with small vectors and matrices and even higher order arrays. However, the way that it achieves that is by specialization, and specifically the size of the array is part of the actual type of the object. And so what this is going to show is something that is maybe not the best use of static arrays, and that is that I'm just going to create a whole bunch of them, but they're going to have random sizes, and I'm going to pack a whole bunch of different random sizes of them into a single vector, and I'm going to contrast that with what happens if you use Julia's regular array class, right? Also of random sizes, but because the size is not part of the type signature, the compiler doesn't specialize on the specific size of the array. And then, so I'm going to profile the actual building process. I think we're not going to look at that. We'll just take a look at the actual then use of these. And so I'm just calling the SVD algorithm on each one. The MD is the dynamic arrays that are all of type array. The MS is the static arrays, where each array has a, well, not each has a different type, but there are many, many different types, up to maybe 64 separate types inside of that one array. And then what I'm doing is I'm going to, not only am I profiling inference with SnoopIDeep, but after the inference process is over, I'm also going to profile a runtime. And the key thing about this is that it allows me to compare the two. Okay, so I'm going to do this. And one of the things I should say is that for these demos, it's sometimes a good idea to do them at the REPL, or you have to turn off some of the, well, it's even better to just simply do them at the REPL, because there's some feedback that you get at the REPL that's hard to get any other way. So I'm launching this. It's building the arrays and compiling the code and collecting the profile data right now. And then if you load the PyPlot package, SnoopCompile loads some interactive plotting tools that you can use to get a sense for where the time is going in all of this. And so it's opened two windows, one for the data when it's of class array, one for the data when it's of class static arrays. On the horizontal axis, you can see the running time, and this is just the self-running time, meaning not including the callees. And this is showing you here the inclusive inference time. You can also show the exclusive inference time if you want to do that. So you're comparing self against self. In the case of array, so each one of these dots is actually a separate method, and the color of the dot indicates how many specializations each one of these has, according to this bar here. So you can see for a lot of these, there may be only one specialization. And in fact, and here's the really nice thing, is if you click on one of these dots, SnoopCompile will print for you at the REPL information about that particular method instance. So here it is. So this is showing you the method, where it's defined, and it's going to count for you the number of specializations. And so this materialize, that was this dot here. I think, no, I clicked on a different one. This dot here is the one that took most of the by far the largest amount of computation time. And you can see it actually spent a little bit more than 10 times as much doing computation as it did being inferred. And so that's a clear, that may be a sign that it was a good thing that we specialized this method, because it still was the main bottleneck in our code, and this is actually in the implementation of the SVD, basically. But again, there's only, I think, one method instance, so one specialization, and that's because all of these arrays have the same type. If you go to, I clicked somewhere funny. Okay, if you go to the static arrays case, you can see the picture is very different. The inference times are much, much longer. The run times are much, much shorter. because you're not using one over and over again. And it's very fast to compute the SVD when it knows some of the sizes anyway, at least for a couple of small sizes. But look at the number of specializations. Some of the dots are yellow, and so if I click here on this one here, let me click on this dot here, you can see now that SVD on a static matrix has 62 separate specializations. So we ended up creating almost all 64 possible sizes of up to size 8, for example. And so you can see in many cases here that some of the inference times are maybe 1,000-fold bigger than some of the than the actual run times. And so this would be an example of what might be a poor decision about the overall design of your package. Because you're not really getting that much benefit from all of the specialization that Julia did. Now, that was, of course, not a very realistic workload, and in general, you want to do this kind of comparison on a realistic workload. Okay, so when you see something like that, where a real computation that you actually care about is dominated by inference time compared to compile time, then you want to see what you can do to reduce the amount of inference that Julia has to perform. And one of the best strategies for doing that is to reduce the type diversity. So the big problem in that static arrays example was that each array had a separate type. It was much better in that particular circumstance to use the generic algorithm that runs on arrays of any size and essentially make all the important decisions at runtime than it was to try to compile a clever version of it for each different size, right? So reducing your type diversity, that often requires a redesign of your package, but it's often the most important thing that you can do if you want to reduce, say, the latency. A couple of other tricks involve things like standardizing arguments for slow-to-compile methods. If you can reduce the slow-to-compile version to essentially a single specialization, that's awesome. And then if you can essentially have other methods of the same function call it just by converting their arguments, then those convert stubs are usually very fast to compile. And in my full talk during the full program in JuliaCon, I'll give a little more of a concrete example of that. There are also specialized tools that Julia allows you to annotate specific arguments. So at no specialize prevents compile specialization and indirectly runtime specialization if it's in a nested call or a non-inferable call. If you do have to actually block inference, you actually sometimes have to use this base.inference barrier to prevent Julia from even no specialized arguments. If they're called inferably, Julia will run inference on that on that method and that argument type. And then finally, if it's not all just inference time, then you often want to tweak some of the compiler options to reduce that. So again, I'll talk about some of these strategies for reducing latency in my overall talk. Today, I'm really focusing on the diagnostics, the tools of how you find out what's going on. Another thing that SnoopCompile can do in order to try to reduce latency is to generate, is to increase the amount of precompilation that your packages do, right? And so one thing that it can do, and I'll show you what this looks like in a moment, is it can generate lists of precompile directives that you can incorporate into your package code. But you don't have to do it that way. And oftentimes it's just as easy to just execute code at build time. And so if you have this kind of statement at top level in your package code, meaning it actually ends up running while the module is being defined, it will force evaluation of foo on this set of argument types, and this will compile foo and those method instances. And let's say if foo is owned by your package, then all of its method instances that exist at the time of module close will also be cached to disk. And so you can force Julia to cache particular method instances for particular types simply by executing the code. Now, you don't always want to do this. A plotting package is a good example where this might introduce undesirable side effects. And so there are many circumstances in which these precompile directives are still very attractive, and SnoopCompile can help you write them, basically. So one of the nice things. Okay, so this was for Flux. I'll do it anyway, even though I have now messed it up. So and we have 60 seconds worth of inference time instead of about 14 seconds worth of inference time, as it would have been if I hadn't tried to evaluate that cell a second time. Okay, and I set this there for way too low. You can set a minimum of how expensive was it to infer a particular method. I set it aggressively before just because I didn't think that I didn't want to make the output for very long. So I reduced it. Nope, there's nothing there. Let's put another 0 in here, or just get rid of it altogether. Nope, this may not work. All right. You can check the, I'm sorry, the Flux thing just took so long. Oh, here we go. Okay, so this is only going to show actually a couple of things here, basically. But what this is showing you here are essentially this is a list of module and then essentially precompile directive lists that it's giving you here. So it actually found some things that maybe would have profited from being precompiled and built into base Julia and in core. If you can always submit a pull request and hope to get those things compiled, but these, as you can see, are very small times, and so they would never be worth trying to get precompiled into Julia base itself. Zygote, and in the other, the full case, the one where I didn't trash the precompile data, is a much more substantial part. And in that one, it accounts for about 4 seconds of the total inference time. And you can see there's now a list of several method instances that it has. In order to make sense of what all of this means, you can write this precompile data to a set of and none of them were precompilable, unfortunately. Anyway, you can write a set of precompile statements, and it will sort through and figure out which ones are actually expected to work out to a cache file, and under normal circumstances, you would be able to see the values there. So I'm, again, really sorry that I hit evaluate twice. But in general, what you get is you get a list of precompile statements, and what would have, one of the things that sometimes happen is you get anonymous functions. And the key point is that sometimes just by browsing the flame graph, you can look up a level from that anonymous function and figure out what the dominant contribution to that is. And so that, you may remember that I mentioned that that there was a single case of a method instance in Flux whose precompilation would have saved about 3 seconds, and you can get that straight from the flame graph. So, okay, so I think, okay, the last thing that I wanted to, yes, the last topic that I wanted to briefly mention is, right, okay, so what were those red bars? So the red bars occur often when you don't own the method. So for example, the sum method, if that was something you needed to precompile, base owns that. Your package doesn't own that. If you're leveraging the actual implementation of this method in base, then you don't own that particular method. Now you may own the types in that abstract vector, but in the end, it's method ownership that is the sort of trigger for considering including a method instance. And so even if you own the types, because you don't own the sum method, you might not be able to cache that particular method to the package, right? Or another possibility is your package may own the method, but what if somebody's using your package and they're passing in a set of types that your package doesn't know about? And this is historically been one of the main challenges to getting good pre-compilation. And for some of you, you may have tried SnoopCompile in the past. I think people are having more and more luck with getting it to reduce latency. I think many times, many of us get at least 2-fold reductions or so when we use SnoopCompile, but sometimes it struggles. And those two problems really crop up there. And so one of the key things to keep in mind, basically, is that when you get some of those red bars, in the case of Flux, those occurred because it was Flux code that was running on a user-supplied function. For many of you, that's a real-world use case that you have to worry about. And there's no way for your package to anticipate every function that users will throw at it. And so this might appear like it's an unsolvable problem. And the good news, it isn't. It's not an unsolvable problem. And specifically, if the user creates a package and they create the functions in the package code, and Flux or whatever is part of that package code, and the user has gone to the effort to make the calls inferable, then it's actually in that consumption package, the one that uses both Flux and the package-defined specializations. Those methods are owned by that package, and because of these backedges, everything will be precompiled there. So for well-designed consumers of your code, what appears to be an unsolvable problem of ownership is actually eminently solvable, but it does require that you solve inference problems. And so that's that's where we'll begin to see more intersection between SnoopCompile and JET, in that both packages have to address this issue of precompilability and all. So with that, I will stop sharing my screen and see if there are any quick questions. And maybe what we should do is we should go on. Shuhei, did you want to go on to the next next stage?
Yeah.
Oh wait, no, sorry. Actually, it's me. Yes. Okay.
Yeah.
yeah. Very good. Okay. All right. So and I will try to get to any user questions a little bit later. Okay. So now we need to. So now we're going to be turning to the next topic of this workshop, and this is really where we'll get into how you diagnose inference problems in your code, because this turns out to be fundamental to an awful lot of things. And so I'm going to walk you through part of this process, and Shuhei will walk you through another part of it. And specifically, the package that we want to introduce and really focus on a lot for the remainder of our presentation is Cthulhu, which is an absolutely wonderful package with a lot of power, but it also has a certain amount of learning curve to it. And so what I'm going to talk about is some of the background that you need to understand what Cthulhu is showing you, and then Shuhei is going to actually demonstrate the use of Cthulhu. Okay, so let me now go back to sharing my screen. Okay. You can see this, I presume?
Yes.
Okay, all right. So what I'm going to talk about is the topic of lowered and typed code, and the notion of code transformation in Julia. For many of you in the audience, I'm sure this is something that you know well. Feel free to stretch and whatever you need to do. But for those of you who don't know this, it's very daunting when you go to start using Cthulhu to see these kind of strange representations of code. And so what I'm going to try to do is take some of the rough edges off for you, basically. And so, as background for why this happens and why it's important, is there are several motivations for it. But one of the most important motivations is that Julia, being a very expressive programming language, often allows you to write things in a couple of different ways that, at least formally, seem a little bit different, right, in terms of the actual expressions that you execute. So, for example, if you want to do a conditional assignment, you can write it like up here, or you can use the ternary expression, right? And these do exactly the same thing. In the end, they would also generate exactly the same code. But at the level of sort of surface syntax, these differ from one another. Another example is in defining functions, right? You can use the verbose long form of defining a function, or you can use a sort of a shorthand for defining a function, right? There are many other examples. Do block syntax, even for versus while loops, those look different, but they kind of do the same thing, etc. And so with all of these differences, if you're writing code to analyze code, this diversity in the way of expressing a particular concept is actually gets in your way, essentially. And so one of the motivations for these code transformations is to simplify the analysis of the code. So the idea basically is you take the surface level syntax that the user, the package developer creates, and you turn it into a form that streamlines it down to essentially the bare essentials, and resolves a number of other issues that make things complicated so that other analysis can benefit. And to give you a hint about what some of these complexities are, consider, for example, here's a function that defines an inner function, right? And so there are specific scoping rules here for where these variables are coming from, et cetera. And some of these scoping rules sometimes make the sort of naive parsing of just expressions is not actually straightforward at all, right? So here I've written a little function, and inside of the loop, inside of this function, the for loop, I've got this variable x here, and then I've got this print line statement here, and then I'm going to call this function. And probably many of you expect the outcome that this will give you an undefined variable error because it says that x isn't defined. And that's because this x is not in the same scope as this x here, right? And so you might initially be confused about that, and if you're writing code to analyze the expressions that go into this code here, then you might indeed your code would have to be fairly sophisticated to be able to resolve all of the scope rules. And so you might imagine, well, then we should just have some standard way of resolving scopes, and indeed we do, and that process is called lowering, among many other things. So basically, the general process of transforming the surface level syntax into a sort of common denominator, lower level code is called lowering. And Julia, because so much of the compiler pipeline is written in Julia, it actually allows you to see the results of this process. So I'll just do a couple of very simple demonstrations to show you what this looks like. So here I've created a function, takes 2 arguments, and very simple implementation. And I'm going to call this function with a couple of arguments. At the level of code lowered, those arguments are only to figure out which method is being called. And of course, in this case, there's only one method. And so what the at code lowered returns is this code info object. And if you've not seen these before, these look quite foreign, but they're actually pretty straightforward. So the first thing I want to call your attention to are these % number lines. These are called single static assignment values, and you can basically think of this as an assignment to a temporary variable. So here it's computing a times a, and it's assigning it to a temporary variable that in the lowered code is being called %1, and then it uses %1 here and it adds it to the b. That's implementing this here, and it stores it in this temporary variable %2, and then your code returns the value %2. Okay, so that's I think fairly straightforward. Not all lines, as you'll see in a moment, actually get these assignments. It's just the ones that you'll reuse the value of at a later point in the code. In the left column, there's another number with this interesting bar here, and this is what's called in compiler parlance a basic block. And basically anything inside of a bracket is a unit of code with no branching inside of it. And so these are essentially the labels for the separate basic blocks that you'll see will make more sense as soon as we put in some kind of conditional and branching. So let's create a function here, g, that takes a conditional input and then 2 other arguments, and depending on if that conditional is true, it will return the sum of those 2 values, and if the conditional is false, it will just return the second of them. Let's see what the lowered code looks like, and what you can see here is that the first line here, which is also the first basic block, there's no assignment, there's no SSA value on the left-hand side because there's nothing here that's going to be saved for a future stage of the computation. But what you can see is it has this go-to statement, and it's going to number 3, that refers to basic block number 3, if the conditional is not true. So in other words, if it's false, it's going to jump down here and just return val2, and indeed that's what our code does. If it's true, then it falls through to the next basic block, and here it assigns to this temporary, this SSA value, the sum of the 2 arguments, and then it returns them. So when it hits this return, of course, it never goes any farther in the code. This goto has the consequence of essentially jumping over that return to make sure it doesn't return the wrong value, but gets to the right one. And so again, this might look initially very foreign, but if you take a little bit of time to look at them, they're not so bad. certain kinds of even loop constructs lower to something which looks quite a lot like the original code. So let's take a look at this function here, which has a while loop which counts down, and then it prints blast off when it gets to 0. And if you look at the code info here, it really looks very similar. It assigns the value 5 there. It tests whether the counter is bigger than 0. There's one of this go to if not statements here. When it falls through that condition, then it prints the counter value and decrements it, and then it unconditionally just jumps right back up to basic block number 2, where it's going to make that test again of whether the counter is 0. It does that until this go-to statement gets triggered, and then it goes to 4, this basic block here, where it prints the blast off. And then it does something that you might not have expected initially looking at the code. It actually returns a value. It's the return value from println, which is actually nothing, so it doesn't really return anything. But nevertheless, you can see that the lowered code makes it explicit. Lowered code doesn't yet know that println doesn't return anything, and so it will return whatever it returns. For loops tend to be a little bit more complicated if you look at the lowered code, and that's because for loops are implemented by calling this function iterate. Iterate returns one of two things, either nothing if there's nothing left to return, and in that case then you go to the sort of exit conditions. But if it's not the case, then this is a two-tuple. One is the item, and then the other is a hidden state variable. And the main reason I wanted to show you this is that this introduces one other bit of notation that looks initially quite strange, and that is that while you can see that many of the variables in this code here, item and SS, for instance, are not passed in as arguments. List is passed in as an argument, but you can see they're listed here by name. Let's see here. Here's the item, making an appearance here. But there's this funny @_3, and this is an unnamed variable, a local variable in your code. This is the return value of iterate, right? And so it gets updated each time. And so SSA values are only assigned once, so you can't assign a changing loop value to an SSA value. Julia introduces a temporary variable, unnamed temporary variable to handle that. And that's all those @ things are. We can use code lowered now to see the scoping rules, and in some ways, once you start getting used to reading lowered code, you can actually see that it's in some ways a simpler representation, or at least it can help you occasionally resolve odd scope issues. So remember that this code actually errors when you execute it, and you can see why more directly here. You can see in this case that X is being assigned the value of main.rand inside the body of this function. But you can see that this X here is being resolved as referring to main.x. And because I hadn't defined a variable called X, then that's where we got the undefined variable error here, right? So this process of lowering also resolves all of the scoping issues and lets any analysis code not have to worry about that anymore, which is a lovely thing. I'm not going to go into this in very much detail, but just to acknowledge the fact that sometimes, even once you learn to read at code lowered, sometimes things can seem a bit confusing. And I'll at least introduce you to some of the complexities there. But again, this doesn't come up as often in practice. But just so that you're aware, some of the Julia constructs have to do more complicated things than they initially appear. So let's look at a case here where we're going to define an inner function, right? And if I do at code lowered, you can say, wow, this is boy, Julia just generates such simple code. It's amazing. You can define this whole lower or inner function with just this little bit, and that's all it takes. But when you start looking at this, you start to get confused because you see this little symbol here. This is a so-called generated symbol. Again, it's one that's an unnamed, not officially named by a human. So the compiler gives it a name, and that's what these hash number symbols are. And then you can see that it actually seems to be building some kind of a type, and it's assigning that to F. And so somehow this F here is actually being assigned an object that's created via some kind of maybe a constructor or something like that. And then you're calling B on that and returning the value. But there's a lot here that we don't see, right? So what is this hash F hash 1, basically, right? And in circumstances where this is actually something important for you to understand, and it often isn't if you're just debugging inference problems, it's worth understanding what Julia is doing. And the way that Julia handles these inner functions is basically schematized here. It actually creates a brand new anonymous structure, basically, the closure structure for that function. And it would look maybe like this. And then it defines a method for objects of the type of closure. When you pass in an argument, then this is what it computes. And you'll recognize this as essentially the body of the inner function, given the fact that A got captured as one of the arguments, input arguments to the function. So Z is being applied as supplied as an argument to the inner function, but A comes from the scope of the parent function. And what's basically happening here is it's getting that value from a struct that gets created to implement this specific inner function. And so that lowered code that you saw actually was just the lowered code for this part of it here. And it was creating the closure object and filling that field with A, and then calling the closure object on the argument that was being supplied and returning that to the user. You can see this whole process, if you are curious, with a more low-level call than @code_lowered, and that's this so-called meta.lower, where you're evaluating it on in a particular module with a particular expression. And so what you can see for this particular case, if we lower this, you can see the result is quite complicated. And I'm not going to go through this in detail for interest of time, but suffice it to say that you get an outer code info object that actually has several internal code info objects. And one of them is a code info object to create the struct. So all of this struct type and set super and type body, all of these are internal functions in Julia for creating new structures, basically. After it's done creating the structure, it has to create that method, this one here that implements the actual body of the inner function. And so there is thereafter a method code info, a method creating code info. And you can see it's got the squaring operation in it with this Z here. So that's implementing that. And then finally, the thing that was returned by @code_lowered is this last part here. And this is the actual body of the outer function, basically, right? So you can see this level of detail if you want. Now, for the purpose of debugging problems of type inference, lowered code is not enough. Each method essentially gets a single lowered code object, but for type inference, you also need the specific argument types. And so, just as a reminder, with this very simple example, this here is what the lowered code actually looks like. The type inferred code, you can get that with @code_typed. And to make it simple, I'm going to first turn off all of Julia's optimizations. And so really the only thing that gets performed is type inference. And when you can do that, you can see it's strikingly similar to lowered code, but with the addition that each operation gets annotated with the anticipated, and as long as type inference is correct, the actual type of each intermediate step in the computation, basically. And so that's what those annotations are there. And then the overall return type of this function is also annotated through this pair syntax. Okay, now, it's interesting to see what happens if you don't turn off the optimizations. And so let's call it now with optimized true, which is actually the default for code typed. And what you can see is that it looks now much more different than it did before. It's still doing all the same stuff. It's multiplying A by itself, and then it's adding B to that result. But you can see it's actually resolved what those arithmetic operations actually call. And so it's actually boiling it, in this case, down all the way to the intrinsics that essentially reduce to CPU instructions, right? And so one of the optimizations among several that Julia supplies to its own code is inlining. And that's essentially what happened here, is that some of those code calls have now been fully inlined. And so there are two views essentially then of type inferred code, unoptimized and optimized. And that's a big big distinction. You can see, of course, that the actual not only are the types that are inferred different, but if you allow Julia to optimize, it recognizes that it has to dispatch to different methods, different intrinsics in this case, when you supply the same function with different argument types. Okay, so but in many ways, once you get used to reading this, it's really not very hard. And as it turns out, looking at this representation, especially if you have some good assist from some tools, really gives you the opportunity to understand at a deep level what's sort of going wrong in your code. And it's a very powerful approach for debugging inference problems. And so with that, I will look, if in the interest of time, I will look in the chat and try to answer questions by text. And Shuhei, if you want to move on to your Cthulhu demonstrations.
Yep, I think we can go to Cthulhu section. And okay, I will share my screen. Okay, can you see my screen? Tim, can you see my screen?
I'm sorry. Yes, I can. I apologize.
Okay. Yep. Okay, let's start a quick dive into JuliaCompiler with Cthulhu. This section will be outlined as this way. First, I will give you an overview and the basic usage of Cthulhu, and then we will take a quick dive into JuliaCompiler and see its interesting behaviors using Cthulhu. We will use these 3 packages for this section, and they should have been installed in, they should be installed into your environment if you followed this section, follow the setup instruction. Okay, Cthulhu can be understood from 2 aspects. One is it's a static walkthrough of a call graph. And the second one is that it's a walkthrough of different program representations. Firstly, Cthulhu is lens into a static call graph, and so it's very similar to code type in that sense. Both of them never execute an input program, while ordinary debuggers will interact with runtime. To illustrate how Cthulhu differs from code type, let's take a look at the following example. So in a function here takes a type and iterator of some objects, and then it sums of values of sums whose type is same as the first specified, same as the one specified as the first argument. Outer function simply calls inner with passing int as the first argument. And we can call it, and we will benchmark it. Suppose we want to improve the performance of outer. It takes some time, but yeah, basically it takes 11 milliseconds at this moment. And we want to improve this performance a bit. So as the first step, as our performance tips suggest, we're going to take a look at what code one type suggests. So let's run code one type on this function call. And yeah, here is an output. So seemingly there is no red line that indicates type instabilities within this function frame. And so the output looks just all good. But yeah, we now know JET test. And yeah, you just give a try to JET test. So JET test is analyzing the call graph, and it reports some type instabilities. So there are type instabilities. What's wrong with code one type? With Cthulhu, we can understand what really happened within this function call. No, static function call. We can use this descend code one type that Cthulhu exports by default, and descend into this function call. So let's go to terminal and see what's happened. Yeah, here is a first output of descend code one type. This is just same as what's a code one type macro output showed to us before. But with Cthulhu, we can descend into a static call of this inner function simply by entering it. And so basically, we descending into a static call and get another code one type output for this function frame. And now we can see there are some type instabilities actually. There are a bunch of red statements, red colored statements. And the important one here is this get property is any typed. And this causes succeeding computations to be type unstable, especially this addition is very type unstable and inefficient accordingly. And this also type conversion also takes some time. With Cthulhu, we can even descend even further. So for example, if we can descend into, so yeah, this get property call, and can understand what's really get property function does. It's essentially just calls get field for this type. But yeah, we can inspect into static call graph like this way. So yeah, what's really happened? I'm going to explain the reason of these type instabilities. With Cthulhu, you can press keyboard S to show source code, and here is a source of in a function. And you can see that these get property calls correspond to these s.value statements here. Expressions here. And the essential problem here is we are branching on the type of s.value object, no, s.value field, but the constraint of constraints that s.value field is t type doesn't propagate it into this Zen block. So yeah, we do need to tell the compiler about that s.value field at this point actually typed as t, and we can make it type stable. So let's go back to our slide, and we can add type annotation as we did in the section of JET, but we can also extract a value field into a local variable, and we can branch on its type. And then Julia compiler can understand the constraints and can propagate the constraint from its call to its Zen block. And now this addition and this addition should be very type stable and will be very efficient. This kind of pattern is quite often used, and it also helps JET to analyze this kind of problem and reduce false positive errors. So I do recommend extracting this kind of field retrieval of object into transforming field retrieval into extracting it into a local variable and branching on its type. So yes, now it runs 2 milliseconds basically, and so yeah, it runs 5 times faster, which is really good. Yeah. Actually, Julia compiler is keeping evolving, and this PR will eliminate the need for this kind of variable extraction in the future. I'm not sure when it will land, but for now we have to extract we have to make this kind of this kind of changes in order to make this programming to be type stable. But in the future we don't need to. So here's a recap. Code type and its family are limited in the sense that they only present the final output of inference and optimizations. With Cthulhu, we can walk through a static call graph by descending into each intermediate state. And Cthulhu itself doesn't suggest anything, and it's up to you how to interpret them. In this point of view, we can think of JET as an automated and opinionated version of a workflow using Cthulhu. So the next aspect. Actually, there are 5 main stages in Julia's compilation process. The first one is called lowering. It takes an abstract syntax tree and transforms it into low-word code. The second one is type inference. It type annotates low-word code and produces unoptimized typed code. The third one is Julia level optimization. It literally optimizes untyped typed code that the step 2 produces. And the next one is LLVM optimization. It basically transforms Julia level optimized code into optimized LLVM IR. The final stage of the compilation process is LLVM's native code generation. So there are 5 different, various different program representations there. One is AST, abstract syntax tree representation of Julia program. The other one is low-word code. We also have unoptimized typed code. We also have optimized typed code. We have LLVM IR, and we even have native code as the final output of our compilation process. With Cthulhu, we can traverse these forms quite easily. You can see, so for example, you can see unoptimized typed code to see how type inference works. And you can also see Julia level optimized code to get an idea of what's Julia level optimization do. And you can also see LLVM IR to enjoy all the tricks of LLVM. And you can even take a look at native code if you doubt all the beauty of programming abstractions. So as an example walkthrough, let's enter this function call. When traversing different representations, program representations of this function call, please note that how inference annotates types and how Julia level optimization inlines function calls, and also note that LLVM further gets rid of array indexing and constant for the final output. So yeah, let's go to terminal again. Yeah, we are seeing with descend with optimize with descend function with keyword argument of optimized to be false, we can see unoptimized typed code. So yeah, we are seeing the IR where type inference annotated types into this code. So yeah, we are seeing those types, those statements are typed, and yeah, we can check how type inference worked on this program. After that, we can press keyboard O and see optimize the typed code. So yeah, Julia's optimizer does a lot of things. Here, basically, its main task was inlining. So it's inlines these higher level function calls into yet more lower functions. Function calls. So there are a bunch of built-in function calls like RI size, and there are really low-level foreign call Julia local 1D, and yeah. So yes, with optimized typed code, we can see the IR after Julia level optimization transformed the unoptimized typed code. So, but we should note that at this point here, Julia optimizer doesn't constant for the output, so it only knows the output is int, and it doesn't understand the final output as constant. Although, oops, in this code, we humans can understand it should return constant 4, but yeah, Julia optimizer couldn't constant fold it. But we can also look at LLVM IR and found LLVM succeeded to constant for the final output, and it returns just integer 4 as a final output. And we can also note that LLVM is not smart enough to eliminate the allocation of RI itself. I think we technically we can eliminate the allocation and further improve the performance, but yeah, LLVM doesn't seem to succeed to eliminate the allocation here. But anyway, it's constant false, and we can understand LLVM optimization. Yep. So yeah, those tools what we can do with Cthulhu, and it's really powerful tool to debug type inference and optimizations that JuliaCompiler does for us. So yeah, as the next part, we are trying to get familiar with JuliaCompiler yet more with Cthulhu. This is because to use Cthulhu effectively, we need to have some basic knowledges of the behaviors of JuliaCompiler. In this part, I'm going to show a selection of most important concepts using examples. Let's inspect this function call. Oops. Yeah, the first one I would like to pick up is dynamic and static dispatch. When looking at an optimized code, there are two different representations of function calls. That is invoke expression and call expression. They indicate the function call is dispatched statically or not. So invoke expression is a statically resolved generic function call, and we can call it as we call it as static dispatch. On the other hand, call expression is a dynamically dispatched generic function call, or it's a built-in function call. So as an example, let's inspect into this function call and see that it's really depending on type stabilities that whether or not JuliaCompiler can resolve a function call at compile time or delays the resolution to runtime. Yeah, please note here, this invoke call is really type stable because we are passing int type as a first argument of this send. And so, yeah, JuliaCompiler can understand a variable a at this point is typed as int, and it can fully resolve the function call of invoke call function here. But on the other hand, here we are using a global variable, which is not constant. And so Julia compiler cannot understand its type correctly. There are a bunch of technical reasons of this behavior, but yeah, important note is unconstant global variable is essentially typed as any. And so accordingly, Julia compiler cannot resolve this function call well. So you can see at this optimizer code, this invoke call is transformed into invoke expression. So this indicates this is a statically resolved. But this main invoke call is a call expression, and it corresponds to this boundary call invoke call function, and it's just dynamic dispatch. Okay, and now we just understood the idea of how JET test works. It's basically just hunts for call expressions appearing in optimizer typed code. So the second important concept of Julia compiler is union split and multiple matching methods. When there are multiple matching methods, Julia's type inference recurses into each matching method, and Cthulhu just follows that behavior. One caveat here is actually this doesn't happen always, because if type inference recurses into too many matching methods, it will really slow down. So inference actually limits the maximum number of matching methods heuristically. But yeah, to understand this behavior, let's use this example and descend into this function call. Yeah, so here we have one single function call, and Cthulhu suggests there is one only single call site. We can, if we enter into this call site, Cthulhu suggests two different calls, possible calls. These two calls correspond to different matching methods here, because there are two methods of multiple m function, and from those signatures, Julia compiler cannot tell which method should be called at this point, because variable I at here can be int, but on the other hand, it can be unsigned int or whatsoever. So yeah, Julia compiler infers into these two different matching methods, and with Cthulhu we can select either of it and descend into the function frame. Yeah. Note that the return type was a union of string symbol. Yeah, this one. Union basically means enumeration of possible types, and Julia compiler will form union when it cannot narrow down the type into one single leaf type. And actually, Julia compiler will split unions into each single leaf type when a call signature includes union type. And this often leads to multiple matching methods. So yeah, we are using this example of what's really, to understand what this really means. So yeah, here this multiple method function call returns a union of string and symbol, and it's passed to this string function call. And so at this point here, our variable is typed as union of string and symbol, and with Cthulhu, we can enter into this string function call and see it's there are two different matching methods. This is because and these signatures is split into two different types. It's a string and a symbol. So this indicates Julia compiler split the union into those two types before trying to find the matching method. And yeah, Cthulhu just suggests this behavior. Yeah. Yet more interesting thing happens when looking at optimized code. That is, Julia optimizer actually will automatically forms either branches, and it automatically expands union split, so that otherwise untyped function calls can be resolved statically. To understand this, we will use this example, and yeah. So please note that very typed functions have really concrete method signature, and still we are passing any type variable to it. So yeah. Oops. Sorry, this example might not be really good. Let me change a bit slightly. I'm going to change it like, yeah. Oh, sorry. Yeah, it should work. So we looked at unoptimized code, but we do want to look at optimized code here. So yeah, this is optimized IR, and we can see there are a bunch of either statements which doesn't appear in the original code, and this indicates Julia compiler automatically forms these either branches, so that these invoke statements can be formed. That is, these invoke statements are the cause of this very typed function, and so even though we passed this variable a as any typed variable, Julia compiler does some tricky thing to resolve this function call statically. So yeah, it's really interesting and tricky hack of Julia compiler. And here is an additional exercise. You can see how method signature affect this automatic union split optimization. It might be interesting if you consider this example together with the fact that our manual says you should use the most general applicable obstruct types for arguments, and when in doubt, omit the argument types. Yeah, it's really true, but you can see sometimes very concrete typed method signature can enable further optimizations. Yeah. The final thing I want to mention here is multi-threading code. To understand type inference and optimizations on multi-threading code can be hard even with Cthulhu. This actually means Julia compiler is also having hard time reasoning about those programs. But anyway, let's consider optimizing this code. This code computes sign values for each integers, but the computation is done in parallel. It works, but suppose we want to improve its performance. Yeah, we can have a look at code one type as always. And yeah, we see core box here, which indicates something got captured by Clojure. And it generally tends to be a source of bad performance, but it's not clear where it actually impacts the performance from this output, because those other problem statements are really typed well. In order to debug this problem, we have to analyze the closure of this closure that this threads at threads macro implicitly creates. With Cthulhu, we can descend into there. So yeah, let's do that. Oops. Yeah, we see the output of the previous code one type here, and we can descend into this threading LAN to see what's happened. And in order to inspect the closure, we have to descend into task call here because it constructs a closure. And we now see the implicit internal constructor of task. And there we see this task call site. And now we see a bunch of type instabilities, actual type instabilities. So there are a bunch of core box here, and this sign function call is typed as any. This indicates a variable named as I is actually captured here somewhat, somehow, and it causes all the type instabilities. So back to the original source code, it actually because really contrived, but this first argument is captured in this here, and it causes all the problem. And actually, this first argument is not used anymore. So yeah, we can just eliminate it, and it should run much faster. If you're interested, you can also use JET test on this function and see those type instabilities. It includes some type instabilities from base, but JET test also understands those type instabilities within them. And now computer science runs much faster because it was previously, I remember, 52 milliseconds, but it's now 3 times faster. Yeah, that's all my Cthulhu section.
All right, thank you very much. All right, we're entering the final stretch. So I'm going to do one last demo. So this is kind of the part of SnoopCompile that we can now talk about now, having introduced Cthulhu. And so let me see here. I guess I'll just do my, oh no, here we go. Yes, I'm going to do all of this in a VS Code window. Can you see my screen?
Yes.
Okay, great. So I am going to start a Julia terminal here within VS Code, and what I'm going to do is I'm going to analyze some very, very simple code. This has an this code has been designed to have something that causes type instabilities, and you'll see the view of what that looks like from the standpoint of SnoopCompile. So here I'm going to load SnoopCompile. I'm going to define a structure, and this is intended to mimic something that you sometimes see in the Julia community, where people use constants and dispatch that in circumstances where sometimes that makes perfect sense, and sometimes you might imagine solving the same problem using runtime computations. And so I'm going to imagine that someone's written a parser here, and they're wanting to tag a bit of text as just plain text. But as a little wrinkle, I'm going to imagine that this is either left, center, or right justified text, and I'm going to envision that the developer decided, for better or for worse, to encode the justification as a type parameter of the aligned text. And so there we go. And so I'm going to load SnoopCompile and define this type. And then I'm also going to create just a very, very simple method here. And in this one, it's just going to create a vector of these. And these are, notice, all left aligned texts. And so if we pass this through SnoopCompile, what you can see is that there is only one direct child here, so that suggests only one entry into type inference. SnoopCompile contains features to record every single separate entrance into type inference, and therefore it can give you an exhaustive picture of every runtime dispatch that occurred in your code. I typically assign this to a variable called itrigs, inference triggers, and that's the name of the function. And you just pass this a t and away you go. And what you can see is that this same texts thing here is the only entrance into inference, right? And of course, you had to go into inference to compile this the first time. So there's really nothing wrong with this bit of code here. Where things get more interesting is if I define this one that creates a vector of heterogeneous types, right? And so if I create that one, and now I do the exact same thing here, now you can see I have 3 direct children, and I do the same analysis of inference triggers, and now you see something here that's a little bit more interesting. I've put in a little bit. Yeah.
Can you increase our font size?
Yes, I can a little bit. Although once I get to the Cthulhu, maybe it will be a little bit harder. Does that help?
Yep. You can increase one size down, I think.
Okay, very good. Thanks. Okay, good. So you can see the coloration is here intended to help you see what's going on. This is the callee. This is saying where it's called from. And then in blue is the specialization of the caller. So it's called from eval. That means I executed it at the actual REPL. Whereas vect was called from 3 texts, and promote type of was called from vect. And you can actually see the specific argument types there. There's a certain amount of effort that's been put onto the ergonomics of this. So for instance, if I wanted to actually go to this source code, I can just edit these inference triggers. So I edit the second one. Here you can see that what will happen is, that normally works. Let me try the third one here. Yes, okay. Oh yeah, it was just delayed. That was all. So you can see it took me to it takes you to the caller, because it's actually the caller that usually is the source of the type instability. And so the first one I had just defined at the REPL. That's why it opened up a little REPL window. But the third one was called from within base Julia, and so it took me to the specific spot in base where that came from. So one of the other things then, so we know that all of these were runtime dispatch calls, right? So both the vect and the promote type of. One of the things that SnoopCompile tries to do is, so I'll show you in a moment that you can use Cthulhu to investigate it, but one of the things that Cthulhu or SnoopCompile tries to do is give you an explanation for what caused the type instability. And I should warn you that it's not always good at this, but it's never, sometimes it's not too bad at it. And it also makes suggestions for how to fix it. And so, for example, in this particular case, for the vect call, it says that the invoked callee is a var args function. And so var args are sometimes sources of type instability. And SnoopCompile tries to suggest some potential remedy. So one is you can just ignore this type instability and move on with your life. Another option would be to homogenize the arguments. And what that basically means is that you notice that SnoopCompile didn't complain about any runtime dispatch when all of the arguments that were passed to vect were of the same type. And that's because inference succeeds in that case. It's only because the types are heterogeneous that the dispatch triggers a separate entrance into inference. So that's one way you could solve the problem. Another suggestion that it gives you is actually the most useful suggestion in this case, and that is to declare an umbrella type, right? And what that actually basically means is that maybe you can put a type annotation on somewhere that would essentially avoid the need for Julia to figure things out. So for instance, if we just simply added this annotation to our code, now in fact it would all be perfectly fine. It would not need that separate call to inference. But before I do that, I do want to show that you can use Cthulhu, and instead of descending into the code, you can ascend into it. And that's because you're basically looking at the callee and then all of its callers. So here from 3 texts. So if I dive into iTrigs of 2, here what you can see is that now this will take a second, of course, but then once it appears here, you can see the call to vect, and it's a var-args call, and it's a var-args of any, so that's why it's red. And then you can see here, and I just hit down arrow on my keyboard, I can navigate to all the successive callers. So if I go to the immediate caller, here I can see the inference results in the 3 text, and in this case you actually get quite a surprise because it actually looks quite decent, right? Everything looks good, and here it knows that it's calling it with exactly these 3 types here, and it in fact knows the output type. This type is concrete even though the element type is not. And if you dive into this, then you also get the surprise of, wait a minute, everything looks totally fine here. What's going on? And so nevertheless, it's not lying to you, it's true. If you load the method analysis package and you say method instances of base.vect, then what you see is that it has actually been inferred twice for these types. One type with the 3 concrete types, but inference also runs on the generic var-arg. And in that case, there's an inference failure, and it's actually this method instance that triggered the entrance into inference, but not this one here, right? And it has to do this ultimately if you passed, for instance, a very long list. Okay, so, but just to show you, I could redefine this function here. And then if I do the TNF again, now I only get 1 direct child, and that's because it doesn't have to try to figure out what type to use for the overall container. I want to just do so this was on creation of these heterogeneous types. I want to show you what things look like if you also then make use of them. So I'm going to define the way that the user might have intended this type to be used, and that is actually do left, center, and right justification on printing the text. And then I'll have some function here which takes a vector of pairs, that's the text and the justification all encoded as a symbol, and we will go and we will see, and you can see, so here we've learned our lesson. We're going to allocate the container output type. We're looping over the inputs and we're creating the objects. We're just, for the fun of it, going to call unique, and then we actually call the alignment here. And if we go ahead and execute this line here now, you can see there are quite a few more direct children. If I collect all of the inference triggers here, you can see the 7 of them. There are 3 that actually came from just simply this line itself, right? It had to create this vector of pairs. There's nothing wrong about these calls. It's just, it so happens that this type hasn't been created in this Julia session before. And since it's being called from top level, it counts as a separate entrance into inference. things get interesting after this call to align pairs, and sure enough, you can see that there are, from this call to unique in here, there are a number of inference triggers. And so again, we can ascend into that, and let's look at the fourth one here. And so here you can again now see another feature of this, which is you can see occasionally in ascend, you'll see a statement, a series of lines like this, and this occurs due to inlining, basically, right? And so if I enter in at this point here, I'm actually entering in at the top level point. You can see that ascend is helpfully letting me, I could select any of these and hit enter, and it would take me to that point in the editor, in my editor, so different lines in the source file for unique. But the other thing then is that if we want, and sometimes just looking at the source code is enough to actually tell you where the problem is, but we can also browse the type code. And this is more like what you just saw in Shuhei's presentation. And so here you can see some of the type instabilities that occurred of this ultimate call to in, basically, okay? And so one of the things, though, that I wanted to emphasize is that I was initially surprised, having written this example, not to see any runtime dispatches for align itself, right? We have 3 separate methods. It can't predict in advance which of these is going to be called, what's going on. And the answer, again, is just union splitting. So if we ascend into that one again, and we take a look here at the call to, let's see here, we take a look at the call to, maybe I can find up here, align, so that's at 37 here. Oh, here it is. What you can see is that there are these 3 types, these 3 options that it knows about here, and it doesn't know which ones they are. Ascend, the point I wanted to make here that's worth making is that actually ascend by default turns off code optimizations. If you turn them on, all of a sudden now you can understand better why things are working the way they are, because you can actually, again, see the union splitting that's going on. And if you wanted to defeat this and actually get SnoopCompile to, or you force an inference trigger for this code, then all you really would have to do, let's just start a fresh session to make sure that nothing has been inferred. And I'll just redefine these same methods here. But I'll also define a 4th method, and it turns out that 4 is the magic number beyond which union splitting and world splitting no longer applies. And so from this point now, if we were to collect our inference triggers, now all of a sudden we would notice some of the other problems with our design. Now we have 11 direct children, and if we take a look at them, you can indeed see that some of them are from these calls to align, specifically the 2 that we supplied as the types of our constructors here, okay? So just again, a summary. Oh, and I can look at the suggest framework for these inference triggers, and you can see that SnoopCompile is fairly good at telling you what type of uninferred call it has. So in some cases, it doesn't know what type to create in advance, and that's a partial type call. Sometimes you can fix those by annotating things. These are unspecialized calls or non-inferable calls. And it has a variety of suggestions for them. Again, don't take these suggestions too seriously because they aren't always best. This is part of why Cthulhu is such a spectacularly useful tool, because it really does let you get your own insight into what's going on. So with that, almost right on the dot, I'm kind of amazed. I think we're wrapping up our session. Just as a brief recap, remember that we introduced quite a lot about the internals of how Julia works, and we believe that this is an important thing to understand and exploit in terms of making all of our packages more robust, more performant, and with lower latency. And so for a lot of these new tools, we're really relying on introspecting into the process of type inference to really figure out what the Julia compiler is doing and how to use the work that it is doing to make concrete suggestions for making our packages better. So that's all I wanted to say. Shuhei, did you have any closing thoughts you wanted to add?
No, I would like to ask you one question from Pigeonhole. Are there any other worth mentioning tools, packages for improving package development that were not mentioned in this workshop?
Oh, I mean, yes, I mean, Documenter is I mean, there are many other ways besides the sort of more, let's say, technically oriented tools that we have been talking about here. There are code formatters that can improve the syntax, and quite a few other tools. Do you have favorites that you like to use?
Yeah, I also say device is a very important tool for developing package in efficient way. So yeah, that's all what I have, and yeah.
Well, thank you. Yes, it's I get value out of it too, even if it takes time to maintain it. So anyway, but yeah, so there are a growing number of tools. Profiling is, runtime profiling is always something to be recommended as a way of trying to improve the quality of the code in your packages as well. And I think what's really nice in part is about the new set of tools is that, like so much of the Julia ecosystem, they are mix and match. So I even posted in the comment section, you can sometimes zoom in on the most problematic part of your code first by runtime profiling, and then using the data that comes back from that to figure out where to start introspecting via JET or SnoopCompile or other tools like that, or Cthulhu, to solve the inference problems. So anyway, so yeah. Okay, I think with that,
we're
done. Thanks everybody for your questions and interests.
Yeah, thanks so much.